Okay, so hi guys. So, in this section of calculus, mostly or more specifically calculus 1, we're going to study limits in this section. So, this is really exciting for me because I love doing these. These are one of my favorite things in calculus. So in reality, of course, I only know that we've only heard the term limit or limit does not exist from the movie Mean Girls. But you might ask yourself, well, what does that even mean, right? Well, this is this whole chapter really is what that's all about. But in this section, we want to define what a limit is really, and these are the objectives. So it says, using the correct notation, describe the limit of a function. It says use a table of values to estimate the limit of a function, or to identify when the limit does not exist. It says use a graph to estimate the limit of a function or to identify when the limit does not exist. And then it says for 2.2.4, define one-sided limits and provide examples. 2.2.5, explain the relationship between one-sided and two-sided limits. And then it says using the correct notation. For 2.2.6, using the correct notation, describe an infinite limit. So the limit as x approaches infinity, basically. And 2.2.7, define a vertical asymptote. Now we know the last part is pretty easy, but we want to know what that means in terms of limits. What does that mean for a vertical asymptote? We know what a vertical asymptote is, right? Vertical asymptote is just when you have a rational function and basically you're doing so. And no, this isn't drawn to scale. This is what a vertical asymptote is. At x equals a. Or you can also have something where you have even exponential functions can have vertical asymptotes. So like, or not exponential functions, but like what I'm trying to say is if you're wondering, like for horizontal asymptotes, exponential functions can have horizontal asymptotes like this, right? Because remember, like e to the x, and we know that basically e has a horizontal asymptote, e to the x, and correct me if I'm wrong. I mean, I at least I believe it does, because it looks like it's approaching a specific number, right? Now, let's look at, you know, you can read this by yourself. Basically, we want to know what, we want to know, before we look at limits, we want to look at the graphs of these functions, right? Now, notice how this one is actually a linear function, but notice that at x equals 2, which is like right here, just right here, at x equals 2, the function is undefined. Now, why is that? Because when we look at x squared minus 4 over x minus 2, if you graph that, you can use the product of, or the how do I say it, the sum and difference pattern to factor the top. And what does that mean exactly for the denominator? Well, here we have a common term of x minus 2, so it's going to cancel out. And it's going to be equal to x plus 2, right? Well, yes, but if you graph the function of x plus 2, and this is just a rough sketch. I'm just doing this really quickly. If you graph x plus 2, you know that this is defined. So basically, let's just pretend that we want to know what f of 2 is, right? If we do it here, we say 2 squared minus 4 over 2 minus 2. We're going to get 4 minus 4 over 0, which is 0 over 0. So f of 2 is undefined. But you have to be careful, because although it is defined for x plus 2, like if you literally just graph f of x equals x plus 2 and you say, oh, f of 2 is equal to 4, yeah, that's true, but we're not looking at x plus 2. This is what it simplifies to, okay? X squared minus 4 over x minus 2 is the one we're really looking at. So do not get confused. This is our real function. If we do, now if we look at x plus 2 and we know that, oh, it does, it does go to x plus 2 though. I mean, yes, it does, but like the limit does. The limit exists. But at x equals 2, it's undefined. Because again, we did it over here. Okay? So really, you have to really be careful. Be very careful when you're doing that, because just because it cancels out doesn't mean that the value at x equals 2 exists. Okay. So for example, if f of x equals x minus c times x minus a over x minus c, then f of x equals x minus a such that x does not equal c. Okay, does that make sense? Like, if I have f of x equals x minus 2 times x plus 2 over x minus 2, then that means I'm going to get f of x equals x plus 2 such that x does not equal 2. So that is why here I get something like this, okay? And actually, hold on. It would be, give me a second, guys. This wouldn't be it. Hold on, give me 1 second. It actually looks, so let me do this again. Hold on. Give me 1 second, guys. So this would be the graph of f of x equals x squared minus 4 over x minus 2. It would be undefined. And this is really just f of x equals x squared minus 4 over x minus 2. It would be undefined at x equals 2. Okay, that's all that means. And then part B, it says that x does not equal, so basically at x equals 2, there's two undefined functions. Now at x equals 2, the function is not defined. Now obviously we wouldn't really know exactly how to like, basically what I'm trying to say is we wouldn't know unless there's a way to actually graph that. Yeah, I mean, you can, but basically it shows three very different behaviors. You see how over here, basically as x approaches 2, it goes over here to like -1. And then over here, as x approaches 2 from the right, it goes to 1. Over here, as x approaches 2 from here, it would go to 4. And then from the left, and then from the right, as x approaches 2 from the right, it goes over here. I will explain what I mean by that later on. This is actually right now, basically. So what does this mean, really? If, for example, I said, find the limit as x approaches, so actually it says it right here. It says, so each of the functions is undefined at x equals 2, but if we make the statement, and no other, we give a very incomplete picture of how each function behaves in the vicinity of x equals 2. To express the behavior of each graph in the vicinity of 2 more completely, we need to introduce the concept of a limit. So remember how I said that is very true, because in pre-calculus, this is why you studied the behavior of functions. When I said, for example, what is the behavior as, let's just, for example, say this function here. What is the limit as x approaches -infinity of this function f of x? Well, as we go more less and less and less in our x-axis, we go more or less, it's going to keep going up in the y term, right? So that means that the limit as x approaches -infinity is going to be, of f of x is going to be infinity. What about over here? As it goes to infinity, it's going to keep going up. Oh, like forever in the positive y value. So what does that mean? The limit as x approaches positive infinity of f of x will be positive infinity. That's all that's saying. It says to express the behavior of each graph in the vicinity of 2 more completely, we need to introduce the concept of a limit. So it says, let's first take a closer look at how the function f of x equals x squared minus 4 over x minus 2 behaves around x equals 2. It says in figure 2.12, as the values of x approach 2 from either side of 2, the values of y equals f of x approach 4. Now, I want to make something very clear, okay? What they mean by approaches, it doesn't mean exactly that it's going to equal, like, in terms of definition, they're not saying like, and this is very difficult to explain, because I feel like a lot of students and a lot of people always think that in terms of a limit, it means that just because the limit approaches 2, or the limit of, for example, 2x minus 1, that, oh, it's going to reach 2, right? So like, if I do 2x minus 1, for example, actually, hold on. If I do 2x minus 1, for example, and the limit, and I'm looking at x equals 2, the limit as, so if I look at my pen and I'm like, oh, the limit as x approaches 2, 2, 2, and let's just say, for example, that I have something like this. Okay. And these two cancel out, right? But also, I know that at x equals 1, it would be undefined. That is, if I have something like that. This would be f of x equals 2x 2x minus 1 times x plus 1 all over x plus 1, right? And in reality, so there is a theorem that says the limit as x approaches c of f of x equals f of c. Yes, that is true. But what they mean by that, they don't mean if you can define f of c, whether or not, this means whether or not f of c is defined. Okay, so that means even if we have something like this, where we don't really, even though, yes, it goes, you know, right here. So basically, we would just say, well, it's not about, we're not evaluating here, basically. That's what I'm trying to say. We're not evaluating the function at x equals c. We are finding the limit as, so basically as x approaches 1 of this function, what happens to my pen as I trace closer and closer to 1? Where am I getting at? What am I getting closer to? Not what am I getting, it's not about what does my y value equal to. What am I getting closer to? What y value am I approaching? Approaching means, so approaching, one thing I really want to make clear, and I know this is really confusing, so I'm trying my very best to explain this as best as I can. When I say approaching, I mean that it's getting closer and closer and closer to 1. So that means 0.99999, the limit. So basically, as I get to f of 0.99999, if I do that, what is my y value gonna be? If you do that on a calculator, right, it's gonna be about 0.99998. Give me a second. Yes. So what does that mean? What if I do 2 times 0.99999? Okay. what is my y value going to be if I do that? Instead of 5 9s, I have 6 9s now. What is it going to be? So if you do that on the calculator, it's just going to be 0.9999998. So what does that mean? It means that it's going to approach 1. If you round this to the nearest 10th or whatever, it's going to approach 1. And now, if I say, for example, well, yeah, I mean, that's basically what it's going to be. And that's what this problem is saying. That's what this all means. And it is hard to it's very hard to understand, because I know when I took calculus, I was like, wait, like if f of 2 or like if f of 2 is undefined, then the limit can't exist. But no, the limit does exist, because it's not about whether or not, even if f of 2 is defined. So let me just try to come up with a theorem, okay? And I'm sure this is a theorem in calculus, but basically, if we have a function f of x, and f of c is undefined, and there is I'm just going to say a removable discontinuity at x equals c, then the limit as x approaches c of f of x exists. Okay. What do I mean by removable discontinuity? That's exactly what we had when we did the 2x minus 1, or not the 2x minus 1, but this other one, the x plus 2, the x plus 2 term. So when we did x plus 2, and we know that at x equals 2, so basically 1, 2, 3, 4 right here, and at x equals 2, this is undefined, and we do 1, 1, 1, 1, 1, 1, etc. And this is the this would be the, I'm just going to try to draw like a really rough sketch. This would be the line. And let me actually fix this part, because when we draw something like this, usually over here, we don't usually do that. So let me fix that very quickly. That means that here, okay, at x equals c, there is a removable discontinuity. Remember when we went over the difference between jump discontinuity, where we have something like this, and then we have like that, and then versus infinite discontinuity, where we have like, I'm just gonna try to make one up. Hold on. So these three, this one, and this one, represent infinite discontinuity. So anytime we have infinite discontinuity at x equals c, then, or not infinite discontinuity, but removable discontinuity. And that's infinite discontinuity. Removable discontinuity means the following. So we either have something like this, or we can have something like this. Basically, where there is a hole at a certain x value where the function is undefined. This is removable discontinuity. So it looks like a function, but at a certain point it is undefined. Now, when it is a removable discontinuity, like I said, then the limit as x approaches c exists. That is if we have a removable discontinuity, okay? Jump discontinuity has more to do with like the limit from between the left and right endpoints, which I will go over later on. But it says this is the definition of a limit. So it says the limit, it says let f of x be a function defined at all values in an open interval containing a, with the possible exception of a itself, and let L be a real number. It says if all values of the function f of x approach, it says if f of x, so if all values of the function f of x approach the real number L as the values of x which do not equal a approach the number a, we can say that the limit of f of x as x approaches a is L. So basically, hold on, so that's what this means. It means that as this, so basically this is L and this is A. This means that the limit as x approaches c of f of x will be L if we have, so even if the function if L does not exist, if the function, like the value L does not exist, if that makes sense, right? I really hope that makes sense, because that's what they're saying, is that basically it would be equal to L. That's if we have any kind of function that does not have a restriction, or it's not that it does not have a restriction, but what I'm saying is if it is a removable discontinuity. Okay. Now for jump, this is why it's very important to understand what removable discontinuity, jump discontinuity, and infinite discontinuity are before we get into limits, because those are also foundations of this, okay? Jump discontinuity means, like I said, when we approach a certain value, we get there, and then we jump and we keep going. Now, if we have a jump discontinuity, so for example, let's pretend we have a graph, right? I'm just gonna say this, and then I'm gonna go, I'm gonna try to go maybe right here. Let this be defined as f of x, okay? Now, obviously, this is a piecewise function. We already know that because, of course, with piecewise functions, they have restricted domains. And it's basically two different kind of functions, but they're pieced together. That's why it's called a piecewise function. But anyways, let's pretend that this is equal to c. So the limit, and let's pretend that this is L, and let's pretend that this one is, I'm gonna say, I'm gonna just say, K. Okay. So what does this mean for we know this is jump discontinuity, right? And I know in the book it doesn't really say this, but yes, the book does say it. I'm just explaining it right now in my own words because this is very important. If we have a jump discontinuity, or if f of x, hold on, if f of x has a discontinuity at x equals c, then there's three things we must keep in mind. The limit as x approaches c from the right side. That means whenever they give you the little symbol here of the plus sign, that means from the right side. And let me actually highlight this to make this a little more clear, because I feel like it's very, very, very important. That's the right side, so basically from this side here, from the right side, the limit as x approaches c from the right side, right, is equal to k, the value k. Okay. And then the limit as x approaches c from the left side. Now this one, what I mean by the left side is this part here. The limit as x approaches c from the left side is going to be equal to, and we're going to say that, actually we're going to say this is equal to L, okay, where k and L are any values of y. Okay. If that doesn't make sense, please let me know. I'm trying really hard to explain that. That means that, so anytime they tell you, like, for example, let's say we have a piecewise function, okay? X minus 2 such that x is greater than 3. So let me see, hold on, give me 1 second, guys. Okay, so actually let's look at this one. So f of x is equal to x minus 2 such that x is greater than 3, and negative the quantity x minus 3 quantity squared plus 0.5 such that x is less than 3. Now let's pretend that we want to find the limit as x approaches 3 from the right side. Okay. How do we do that? Okay. Now, again, we can try to sketch it. We know that when x equals 3, or when x is greater than 3, we can basically do So basically the first one is defined, right? X minus 2 is defined. And we know that when x is less than 3, so that means that, or actually, hold on, it would look like this. So when x is less than 3, basically this, it would kind of look, let's see, give me 1 second. So when x is less than 3, this would be the other one, right? Now we want to find the limit as x approaches 3 from the right side. If we grab our pen and look at this part, what is it getting closer to? It's getting closer to 2. Or actually, hold on. To 1. Let's pretend that this is 0.5. And this is 1. So it's getting closer to 1, right? So the limit as x approaches 3 from the right of f of x is equal to 1. And the limit, and what about the limit as x approaches 3 from the left? If we do that one, from the left it's getting closer and closer and closer to about 0.5. So the limit as x approaches 3 from the right of f of x equals 0.5. Now sometimes they're not going to give you a, when finding a limit, they're not going to give you, what is it called, like a, they're not going to give you a graph, okay? Sometimes we're going to have to do this without looking at the graph. So let me try to do another one without a graph, okay? So let's pretend I have something like this. And I want to know the limit as x approaches 3 from the right. Without doing a graph, it's still possible to do this. So if you really try to think about it, like you have to use your brain a little bit. The limit, so when they say the limit as x approaches 3 from the right, you have to ask yourself, what is to the right of 3? If I do a number line, I have 1, 2, 3 over here. What is to the right of that? Well, it's going to be 4, 5, 6, ... So basically, as x approaches 3 from the right, let's pretend that that I do 4.1, and then or actually, hold on, 3.1, right? And I say, okay, what is 3.1 minus 3? Because that's where, because I know that 3.1 is greater than 3, right? So I say, okay, that's 0.1. And, or actually, my bad, minus 1, excuse me. That's 2.1, right? Well, what about 3.01? Well, 3.01 minus 1, that's just 2.01. What about 3.001? 3.001 minus 1 is 2.001. And if I keep going and going and going and going, if I say 3.000000001, I can say, okay, this is 3.000000001 minus 1. This is 2.0000001. So what does this mean, really? If it's going to keep adding zeros, what will it approach? it's going to approach 2. It's going to get closer to 2 eventually. It keeps getting closer and closer and closer to 2. And that is what we have to remember, is that whenever we see something like this just means that it gets closer and closer to the very front value. Okay? And so therefore the limit as x approaches 3 from the right of f of x is going to be 2. And again, like I said, just because, so if it's from the right, that doesn't mean that, I mean, we can do the limit as x approaches 3, but that doesn't always work for every function, you know? Basically what I'm trying to say, that the limit as x approaches a from the right is not, of f of x, is not always equal to the limit as x approaches a of f of x. And I say that because here, for x equals 3, we have the limit is 2 different things, right? Now, let's say that it told me to find the limit as x approaches 3 of this function. Well, what am I going to do? I mean, I know that, so for x is less than 3, as basically I have something like this, because it's a what is it called? Actually, no, I have something like this. It's a negative cubic function. But for x is less than 3, or x is greater than 3, excuse me, it gives me something like this. So you ask yourself, well, what is the limit as x approaches 3? Because obviously it can't be this one, because this is from the right. Obviously it can't be this one, because this is from the left. So if I redraw this, if I say this again, let's pretend we have something like this. Actually, hold on. Like that. And we know that this function is f of x, so the limit as x approaches c of f of x, in reality, from the right it goes to k, from the left it goes to L. So what does that mean? That means that the limit does not exist, okay? Why? Because it's approaching 2 different numbers. How am I supposed to know how it, like, if it only approaches c from one side? Because the limit as x approaches c of f of x is not equal to, or actually from the left side, is not equal to the limit as x approaches c from the right side. So what can we conclude about that? That means that if the limit as x approaches c from the right is not of f of x is not equal to the limit as x approaches c from the left side of f of x, then the limit as x approaches c does not exist. This is something we must remember, okay? It's very important because obviously, I mean, anytime you have something like this, I feel like a lot of people, they think, well, it's going to be two things, but no, it's not. A limit can only approach one value. It cannot approach 2 values of y. Otherwise, it wouldn't be a function. Because remember when I said that if we have a function like this, or let's say a circle, okay? right here and right here, if this is x equals c, and this is, I'm just going to say f of xy, even though I know this is not multivariable calculus. I can say the limit as xy approaches c is equal to, well, it's going to be this, L, and then this is, or not this, hold on. This is K, so then it's like, well, as x approaches C from one side, it approaches two things, so it does not exist. Okay? That's what I'm trying to say here. You have to really think about it. And like I said, and I will say this right now, if anybody has any questions, I know this is, for me, it's a little bit difficult to explain because I know that when I first learned this, it was confusing, but we must not overthink it. This just means from the right. This one means from the left side. And that means if the right side, if the limit as x approaches c from the right side is one thing, and the limit as x approaches c from the right side is another thing, then the limit does not exist. It's really something that we must understand. And if you really don't understand it, at least, we can memorize it. That's at least what I would do. Okay, hold on. Give me 1 second, guys. Let me see if, hold on. Okay, so, for example, looking at the limit as x approaches 0 of sine of 1 over x, we call this something. There's something, it's called oscillation, oscillates, meaning that it keeps oscillating when a function oscillates. So for example, f of x equals sine of 1 over x. Okay. Then what does that mean for the limit? If f of x oscillates, at least I think, then the limit if f of x oscillates at x equals c, then the limit at as x approaches c of f of x does not exist. That's why here it keeps going up and down, up and down, up and down. So it's like, what does it really equal to, right? It can't equal it. It's impossible. So the limit does not exist. Okay. Let me try to see. Hold on. So this is what so basically this is what I meant by one-sided limits. One-sided limits, like I said, are just these. These are one-sided limits. The limit as x approaches c from the right versus the limit as x approaches c from the left. This is one-sided and this is one-sided. Okay? That's what that means. So, and they use that example of x approaches 2 from the right versus x approaches 2 from the left to evaluate the limit as x approaches 2 of x squared minus 4 over x minus 2. I can actually work that out. So for example, I can say, okay, what about what is the limit as x approaches 2 from the left? Well, if I do the limit as x approaches 1.9 of the absolute value of 1.9 quantity squared minus 4 over 1.9 squared minus 2, or 1.9 minus 2, excuse me. This is going to give me, so let me see, hold on. So this is, the limit as x approaches 1.9 of this function will be 3.9. Now what if I do the limit as x approaches 1.99? So if I do that, the top part would be negative, so it would be 1.99 quantity squared minus 4, the absolute value, over 1.99 minus 2, right? Which is negative 0.01. This is equal to the absolute value of negative 0.0399, and then we would say over negative 0.01. And if I do the absolute value of that, it would be 0.0399 over negative 0.01, or 1/100th, right? And so it would be negative 3.99. So again, that means that as I keep going like 1.99999, as I keep adding more nines, it's just going to keep adding more nines over here. So what does that mean? That means that the limit as x approaches 2 from the left is going to be negative 4 eventually. That's what it's going to eventually reach. I mean, approach, excuse me. It's going to approach that limit, not reach, because obviously if we do 4 squared minus 4 over 4 minus 2, that's, or not 4 squared, 2 squared minus 4 over 2 minus 2, that's 0 over 0, so it won't actually be defined at that point, but it will, the end behavior of the graph will reach that point as x approaches 2. Now, as x approaches 2 from the left, excuse me. Now what if I did it from the right, though? Well, I can say this is, this is 2.1, so the limit as x approaches 2.1 of the absolute value of 2.1 squared minus 4 over 2.1 minus 2. This will be equal to, and let me go ahead and do that in the calculator. Okay, so let me just explain this part. Obviously, if I do it from the right-hand side, so you see how from the left-hand side it's negative 4, the limit as x approaches 2 from the left-hand side is negative 4. Well, from the right-hand side, the limit as x approaches 2.1 is obviously 4.1. And if I keep going, no matter how many zeros I add of x squared minus 4 over x minus 2, of the absolute value of x squared minus 4 over x minus 2, this is going to equal to 4.000001. So it's going to be 4. So the limit as x approaches 2 from the right of the absolute value of x squared minus 4 over x minus 2 will be 4. And the limit as x approaches 2 from the left of the absolute value of x squared minus 4 over x minus 2 is going to equal -4. So the limit, because it's equal to two different things, the limit as x approaches 2 from either left or right of x squared minus 4, of the absolute value of x squared minus 4 over x minus 2 does not exist. Okay? Because it's approaching two different numbers. Alright? You see, over here, it's approaching two different numbers from the right as x approaches 4, or as x approaches 2, excuse me. It's approaching 4, and then from the left, it's approaching -4. So really, the limit as x approaches 2, that means that it does not exist because it's saying that y equals 4 and y equals -4, and we can't have two y values like I said earlier. Okay. It says, let f of x be a function defined at all values in an open interval containing a, with the possible exception of a itself, and let L be a real number. So it says, okay, so this is true. The limit as x approaches a of f of x equals L if and only if the limit as x approaches a from the left of f of x equals L, and the limit as x approaches a from the right of f of x equals L. Okay. Now infinite limits, infinite limits are another thing. So let's see, hold on. So you could do the exact same thing that you learned for like the table, like doing the table like this from both sides. You can do that also for infinite limits, right? So like the limit as x approaches 0, or not infinite limits, but the limit as x approaches 0 of f of x being that it gives you a function where you would have 1 over 0, right? Now these are very important. So it's saying if n is a positive integer, then the limit as x, or a positive even integer, then the limit as x approaches a of x of 1 over x minus a to the n power equals positive infinity. So that means that if I have, for example, the limit as x approaches 0 of 1 over x minus 0 raised to the second power, then that means that this will be positive infinity. So the limit as x approaches 0 of 1 over x squared is really just positive infinity. If I say the limit as x approaches what would it be? It would be I'm trying to think, actually. Hold on. As x approaches 3 of 1 over x minus 3 squared, that would just be positive infinity. Now, if I said, now for odd integer, it's saying that the limit, if it's an odd integer, so listen very carefully. For example, the limit as x approaches a from the right of 1 over x minus a quantity cubed of this is going to be equal to, it's going to be equal to positive infinity. And the limit as x approaches a from the left, that means from the left-hand side as we get closer and closer to a, the limit as x approaches a of x minus a raised to the third power from the left side is going to be negative infinity. That is because, for example, if we look at 1 over x, and it doesn't have to be 3, it can be 1 over x minus a raised to the n power, where n is odd. So if we look at 1 over x, for example, I'm trying to think, hold on. Yeah, if you look at 1 over x, for example, basically, so the limit as x approaches a, so let's pretend that, or actually, hold on. Let's pretend that it's like this, and this is a, right? That means that the limit as x approaches a from the left-hand side of f of x is negative infinity, and the limit as x approaches a from the right-hand side of f of x is going to be positive infinity. Okay. Now if it were cubed, and I think I know how to do this one. Hold on. Like this is where n is odd. This is 1 over x to the first power, and 1 is odd. Okay. And then if I had to the second power, I think it would look something like this, if I'm correct. Okay, and n is odd. That means that the limit, or actually, no, I'm lying, where n is even, excuse me. The limit as x approaches a, for example, limit as x approaches 0 from the right-hand side of f of x is going to be positive infinity, and also the limit as x approaches 0 from the left-hand side is also going to be of f of x, meaning that this is f of x, is also going to be positive infinity. Okay, that's all that's saying. That's really all this is saying. Okay, so these are more limit rules, and like I said, it's really important to not overthink it. Okay guys, so for this last part of the video, what I want to do, and I want to look at this problem here, this problem right here, where we're given this graph, and I promise this is the last part of this video. I really want to make sure that we understand exactly what this means, right? Now, it's saying to say whether each of the following is true or false. For the first one, it says, the limit as x approaches 10 of f of x is equal to 0. Now, if we, again, like looking at the right-hand side, we can go up to 0, or up to 10, excuse me. And then from the left-hand side, we can go down to 10, right here. So yes, that's true, because right here, there's no other specific value that 10 is approaching, or that f of x is approaching as x approaches 10. Now it says the limit for number 47, so yes, the first one is true. 47 says the limit as x approaches -2 of f of x from the right-hand side is 3. So again, you're going to go from the right-hand side, go all the way to -2, x equals -2, so you're going to go like this, like this, like this, and you see that it goes up, 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 and you're like, wait a minute, no it doesn't, it goes up to infinity. Now don't be fooled. This one here, this curve here, is the limit as x approaches 2, or -2 from the left. So number 47 is false, because it's actually from the right-hand side, it's approaching infinity. From the left, it's approaching 3, not from the right. From the right, it's approaching infinity. So this one is false. Now, the number 48 says the limit as x approaches -8 of f of x equals f of -8. Okay. F of -8 is right here. That means that f of -8 is 3. -3, excuse me. But the limit, if we look at the curve, the limit as x approaches -8 is actually -6. So no, this is false, because -6 does not equal -3, okay? Now, the limit, the last one says the limit as x approaches 6 is 5. So let's look at the left-hand side, okay? The limit as x approaches 6 of f of x, it goes to 2 actually. And the limit as x approaches 6 from the right is 5. But the limit overall as x approaches 6, it's approaching 2 different numbers. So it does not exist. So this one is false. Okay? Let me see. Hold on. So let's just do this last part, and that'll be it for this video. I know I made it pretty long, and I do apologize. But yes, I really just want to make sure we understand this. So looking at this function, and let me actually, hold on. Let me actually do something really quick. I'm going to just go ahead and do like this. Okay. So here it says the limit as x approaches -2 from the left of f of x. So what we're going to do, we're going to go from the left-hand side. We're going to trace our pen like this. And we see that it approaches 0. So this one is equal to 0. Now it says the limit as x approaches -2 from the right. So we're going to go from the right-hand side. We're going to go to -2. This one approaches 2. And then 61, it says the limit as x approaches -2 of f of x. So again, you see how it's approaching two different numbers? The limit as x approaches -2 from the left of f of x does not equal the limit as x approaches -2 from the right of f of x. So thus, the limit as x approaches -2 of f of x does not exist. This one does not exist. And then it says the limit as x approaches 2 from the left. So let me do this again. Now we're going to 2, not -2. So we're going to go down to 2 from the left of f of x. It's going to go to -2. So the limit, so this one is -2. And then it says the limit as x approaches 2 from the right. So from here, we're going to go down to 2. So we see that here from the right, it approaches 2 because it's from the right-hand side. Okay, so here it's going to be 2. And then the limit, so the overall limit as x approaches 2, it goes here and then it goes here. So it approaches two different numbers. So the overall limit, because the limit as x approaches 2 from the left of f of x does not equal the limit as x approaches 2 from the right of f of x, then the limit as x approaches 2 of f of x does not exist. So this one does not exist. Okay, guys, I believe that's it for this video. I know I made it a little bit too long, but like I said, I really wanted to go over, limits and just try to really understand limits and the table form of limits and all that stuff, because it is very important that we understand that, especially going into this chapter, okay? So with that being said, guys, if you watched all the way to here, thank you so much for watching. If you have any questions, again, like always, please let me know. I know this section was a little bit tough. It kind of was. And if you're confused, again, like I always say, please let me know down below. And if you need clarification on something, I will be more than happy to do that. But with that being said, guys, thank you so much for watching, and I will see you guys in the next video. Oh, and please like, comment, and or subscribe to my YouTube channel. Thank you so much, guys. Bye-bye.